Hi everyone, thanks for joining us for this session. This session is the GCSE Physics session, and we're going to be covering forces in motion. It's going to be delivered by the wonderful Preshayla, who's one of our tutors here. Preshayla is currently studying physics at Loughborough University, and she has delivered a lot of sessions with us. For newcomers, throughout this session is an hour in length. And it's normally broken down into 45 minutes of content where Preshayla would just kind of go through the content that she has for us today. And then at the end, there'll be 15 minutes for a quick Q&A. That being said, you can drop any questions that you have within the chat function or within the Q&A pop up at the bottom of your screen, and myself and Preshayla will just try and pick it up as we go along. I will give it over to you, Preshayla, if you're ready.
Cool. Okay. So what we're going to cover today is the second part of the specification for forces in motion. So I've had to split it into two parts because it is such a big topic, and it will be carrying on into next week as well. So we'll be doing a little bit more on moments. We'll cover the required practical next week as well, and we'll do a summary of all the forces. But what we'll be covering today is understanding what resultant forces and Newton's 3 laws of motion. We're going to understand stopping distances, thinking distances, and braking distances. So all about cars and vehicles and how they move and how they behave. Understand reaction times and the method that we use to calculate them, go through a few example questions, just consolidate what you've learned today, and then we'll have time for questions as always at the end. Okay, give me 2 seconds. I just need to re-upload the PowerPoint because it kicks me off.
Preshayla, whilst that's loading, we just had a quick question of whether you could quickly give a recap of the last lesson.
Yeah, of course. Okay, so yesterday we did the first part of forces in motion. We talked about speed, acceleration, and time. So we talked all about our kind of new equation for speed, distance, and time, which is S equals VT. So distance equals speed times time. But it is a little bit confusing because now we have different letters. So S is now actually distance, V is now velocity, and T is time. And that can be confusing because S, we might think that it means speed, but actually S is displacement. So it's the vector version of distance. Okay, and what that basically means is vectors and scalars are two different things. And we talked about the different kind of what is different between scalars and vectors. So we talked about scalars being just a value, so they just say the speed, the distance, the value with the unit. But vectors are the value with a direction. Okay, so they're the value with a whole direction. So we can't just say the value, we need to also put a direction on. So for example, 6 kilometers north, 6 kilometers west, whatever it happens to be, there needs to be a direction attached to the vector. Okay, so that's what we talked about yesterday, is the difference between scalars and vectors. We then went on to talk about acceleration, and we had 2 equations that we can use to work out acceleration. The first one was the change in speed divided by time. So that was, I'll just write it on the board. So that was A equals delta V divided by T. So that was our first equation that we used to work out acceleration, where delta V is the change. So that delta is that triangle, which means change in velocity. So final velocity minus initial velocity. What is the change in the velocity from point A to point B divided by the time? So that's the majority of what we covered yesterday. We also covered a SUVAT equation. Now, don't worry if you don't know what SUVAT means. It's not important for GCSE, but the equation that we did was V squared minus U squared equals 2AS. So this is a new equation that we've brought in, and it's a different way of calculating acceleration. So it's a new equation, a new way of calculating acceleration, but this time with different terms. So it really depends on what the terms that you have for the equations that you use. We also talked about distance time graphs and velocity time graphs, so what the features of each of those mean. I won't go through it now, but it is important that you know the features of those two graphs. If you did want a more in-depth summary, then just do go and have a look at the webinar, which should be uploaded to YouTube. So starting with what we're going through today, so we're going to start with the Newton's laws of motion. So the first law of motion is an object will remain at rest unless it's acted on by a force. And it seems really simple because that's obvious, right? If an object is just sitting there, unless you touch it, it doesn't move. That's the first part of Newton's first law of motion. If an object is stationary, it remains stationary until it's acted on by an unbalanced force. What that means is, basically, if we hit it, if we kick it, if we cause any sort of motion, if we put any sort of force on it, then that's an unbalanced force. So we move the object out of its stationary balanced position and we put a force on it so that it moves. Okay. Now, an object in motion continues with constant speed and direction unless, again, it's acted on by an unbalanced force. So let's say we've got a ball flying through the air, you've just kicked the ball, it's flying through the air. That's going to carry on with constant speed and direction until a force acts on it. Now that can be a number of forces for a ball. It could hit another player's foot, that's a force. It could hit the goal, that's a force. Gravity could act on it, that's a force. Air resistance can act on it, that's a force. The weight of the ball itself. So lots and lots of different forces that act on this ball. Okay. But ideally, that ball carries on in motion forever with constant speed and constant direction. But realistically, there are going to be forces that act on that ball. That means that it doesn't continue forever with constant speed. So something like it hitting a goal, it hitting the ground, it hitting a foot, its weight just bringing it back down to earth. They are all forces which can change the motion of the ball. But if the object is moving, the object continues to move at the same velocity. Another example is a vehicle. So let's take a car, for example. The car is driving along a road, constant motion, constant speed, right? You're putting your foot on the accelerator pedal, you're letting it go with constant motion, constant speed, constant direction. Unless you put a force on that car to slow it down, it's going to carry on. Okay, and examples of forces that might change the motion is the brakes. So when you press the brakes, the object no longer moves with constant speed and constant direction, it slows down because it's been acted on by an unbalanced force, which is the brakes. Okay, so that's kind of the basic definition of the first law of motion. So if the object is stationary, the object remains stationary. if the object is moving, the object continues to move at the same velocity, remembering that velocity includes both the speed and the direction. Okay, so that's the first law of motion. Now, if you are higher tier, you need to know this bit in blue, which is the tendency of objects to continue in their state of rest or of uniform motion is called inertia. Okay, quite a complicated statement there, but basically what it means is that the reason that things kind of tend to stay the way that they are is because of inertia. So you just need to know this key term, inertia, which means that it's kind of the reason that things tend to stay as they are. So stay stationary if they start stationary, stay moving if they are in motion. Okay, so resultant force. You might have heard of this word, resultant force, but a lot of the students I tutor actually have no idea what resultant force means. They know that it's obviously a force and that it's very important in Newton's second law of motion, which we're going to go on to. Actually, what does it mean? So when two forces act on an object and they are not equal in size, they are unbalanced. Okay? Now, the overall force acting on the object is called the resultant force. So let's say you'll get a really, really big pull from this side, but not much pull from this side. So it's pulling it that way. Okay, so you pull a lot on the right-hand side, not a lot on the left-hand side. So the resultant force is going to go to the right because there's a bigger force acting that way. Okay, so they're unbalanced. The net force, the bigger force, is in the right direction. So the resultant force is in the right. Okay, so another example is a car moving. So let's say the car is accelerating. Well, the forward force is therefore much bigger than the resistive force. Okay, so with a car moving, it's accelerating, it's getting a really big force in the forwards direction, but not a lot of force in the resistive backwards direction. So the resultant force, the overall force, kind of the bigger force, moves in the forwards direction. So the resultant force is in the forwards direction. Okay, hopefully that makes sense. So it's kind of the force which pulls it in the direction of motion. So if a car is moving forwards, the resultant force is in the forwards direction. Now, if a resultant force acts on an object, the object accelerates in the same direction as the resultant force. So let's say we've got a box and we've got two kind of ropes attached to either side of the box. So our box is here, we've got a rope attached to this side and a rope attached to this side. Now we pull really hard on this side to bring the box forwards. Okay, that is the direction of our resultant force. It's the bigger force, it's the overall force. It's much bigger than the resistive force. So we pull it. That is the direction of the resultant force. Now the object accelerates in the same direction as the resultant force, which makes sense. The way that we're pulling it, the bigger force is obviously going to go in that direction. It's going to accelerate in that direction. Okay, so our force is coming from this side, so our acceleration is also going to go that way. So we need to know this rule to understand Newton's second law of motion. So the rule is, if a resultant force acts on an object, the acceleration of the object is in the same direction as the force. So Newton's second law of motion is F equals ma. You might have heard of it before. F stands for force, m stands for mass, a stands for acceleration. So this is our third equation that has acceleration in, but you can start to see that all three equations have different features and different key terms in them. So this one you'd use if you had mass and force, mass and acceleration, or acceleration and force. If you have any of the two quantities, you can work out the third. So Newton's second law of motion is defined as the acceleration of an object is proportional to the force acting on the object and inversely proportional to the mass of the object. So what does this proportional and inversely proportional actually mean? Well, proportional means that if one thing changes, the other thing changes in the same way. So let's say we have a constant mass. Most of the time we are going to have a constant mass. There is not many cases, I mean, I don't think there's hardly any cases that we come across where we've got an object and the mass is changing constantly, right? Most objects tend to have a constant mass. So this law of motion assumes that our object has a constant mass, which is an appropriate assumption to make. Now, proportionality of acceleration and force means that if force doubles, acceleration doubles. If force triples, acceleration triples. If force is halved, acceleration is halved. So whatever happens to force happens to acceleration in the exact same way. But it's not applicable for addition and subtraction. So if force adds 5, acceleration doesn't necessarily add 5. If force minuses 4, acceleration does not minus 4. That's not how it works. It only works with multiplication and division. Okay, so force doubles, acceleration doubles, and it's all related with our constant mass. Some people like to think about proportionality with numbers, and I certainly do. So hopefully this might make more sense if what I just said didn't make sense. So let's say we have a constant mass of 2. Our mass never changes. We have an acceleration of 4, so our force is 8. Now we have the same mass, remember mass never changes, but we double our acceleration to 8. So we're doubling our acceleration from 4 to 8. So we have to double our force, which is 16. Okay, so if you double acceleration, you can clearly see that you double force for a constant mass. So the mass stays as 2 kilograms, but if we double acceleration from 4 to 8, we double force from 8 to 16. And this works with any multiplication factor and any division factor. Okay, so that's proportionality, but what about inversely proportional? Well, inversely proportional works in a different way, which says that if force, so acceleration is inversely proportional to the mass. Acceleration is inversely proportional to the mass. So that means if the acceleration changes, let's say by a factor of 2, the mass is halved. Okay, so if the acceleration is doubled, then mass must be halved for a constant force. Okay, so inversely proportional works in the opposite way. They no longer do the same thing, they do the opposite thing. So if one times is by 2, the other one divides by 2. One times by 4, divides by 4. And it doesn't need to be doubling all the time. It can literally be anything, times by 100 if you want. Okay, so that's what proportional and inversely proportional means. And it comes up a lot in lots and lots of different physics equations. So it is important that you know what proportional and inversely proportional means. Now, somebody asked for it in a triangle. So if you like to learn your equations in triangles, F is going to be at the top, M is going to be here, and A will be here. So F divided by M is A, F divided by A is M. Okay, so that's the second law of motion. Now, again, if you are higher tier, you need to know all about inertial mass. So this idea of inertia is how hard is it for us to actually change the velocity of an object? Is it easy? Can we just throw it and the velocity changes? Can we just knock it over and the velocity changes? Or is it hard? Do we have to put in a lot of effort to make it go faster? So for example, me throwing a ball is much easier to make the ball accelerate than me in a car trying to make the car accelerate. Right? I have to put more effort in to accelerate a car than I do for a ball, which makes sense because the mass of the car is much higher than the mass of the ball. So I have to put more effort in to move a bigger mass. But we call it the inertial mass. It's very, very similar to mass, but it's more thinking about how difficult it is to make the object move. Okay. Now the inertial mass is defined as the ratio of force over acceleration. So the ratio of force over acceleration. Remember, ratio is just a division. So F divided by A is the inertial mass. Okay. Now, objects with a greater mass have a greater inertia. That's the first thing we need to consider. So a car is going to have a much greater inertia than a tennis ball, right? Because it has a greater mass. That's how inertia works. And so a greater resultant force will be required to cause the same acceleration. So let's say I wanted to accelerate the ball by 3 meters per second. And I want to accelerate the car by 3 meters per second. It's going to take me much more force to get the car to accelerate than the 3 meters per second squared than to get the ball to accelerate 3 meters per second squared. So hopefully that makes sense. I have to put loads more effort in to get the car to accelerate the same amount I have to get the car to accelerate the same amount as I need to get the ball to accelerate. But I need to put more effort in to cause the same acceleration because it has a greater mass and it has a greater inertia. Just think about it from kind of an experimental point of view. So think about you doing it yourself. If you ever get confused, a great way to think about physics is just take yourself away from the maths, take yourself away from the exam board, all the specifications, all the formal definitions, and just really think about yourself experimenting with these definitions. So just think about, oh, if I did have a car and if I did actually have a tennis ball, it's obviously going to make me, I'm obviously going to have to put more effort into the car, right? Because it's harder to move. It's got a greater mass than I'm going to have to do with a tennis ball. So just take a step back, think about it realistically, and that's going to help you to level with yourself and help you to kind of come back and form a proper definition. Okay, so it's a great way to think about physics. So for objects with a greater mass, like a car, we have a greater inertia, therefore we have a greater resultant force needing to cause the same acceleration in, for example, another object that has a lesser mass. Okay, so that's all about inertial mass. Don't worry about it if you're not higher tier, but if you are higher tier, it's a very important topic in forces of motion, and they like to test it a lot. Okay, so moving on to Newton's third law of motion. So Newton's third law of motion is whenever two objects interact, the forces they exert on each other are equal and opposite. Okay, so they exert on each other are equal and opposite. So we've got 4 examples here that you can see. If you were to put your finger on a ball, I don't know why you do that, but it's just an example. So if you put your finger on a wall, you are pressing against the wall, but the wall is also pressing back against your finger. Now, it might not feel like there is a reaction force coming into your finger, because obviously our finger doesn't move, but there is. Okay, so it's kind of an abstract idea to think about because we never really feel it. So whenever two objects come into contact, there's a force both ways. So for example, we've got a swimmer here and her feet are touching the side of the pool. She's going to push off to the left. So she's going to push off this way. And obviously there's a force bringing her forwards when she pushes off. But there's also a force of her feet against the wall. So there's also a force going into the wall, not just a force going out of the wall. Okay. The same thing with a skateboard. You're making the skateboard go forwards, but the skateboard has also got a reactional force that makes it go backwards. And then the really, really kind of simple basic idea is if we have any object lying on a table, lying on the surface, even that has an action and a reaction. So for example, the action would be the weight, but the reaction would be from the table. So let's say you've got a water bottle on a table. The water bottle has a force on the table, which is its weight. But the table also exerts a force on the water bottle. So it works both ways. We no longer are thinking about forces in a one-sided way. We now need to consider the other force that we can't see, that we don't feel, but is there. Okay, so let's say two people bump into each other. One exerts a force on the other, but there is also a reaction force from the other person. So any two things that are in contact for however short amount of time, for however long amount of time, have an equal and opposite force. So an action and a reaction. Okay, so that's Newton's 3 laws of motion. I'll just go through them again, just quickly summarizing. So the first law of motion is this idea that if an object is stationary, it stays stationary, unless we put a force on it. Pretty simple. We see this every single day. Everything stays as it is, unless we move it. Unless we put a force on it, we kick it, we hit it, we pick it up. Yeah, so everything stays stationary until acted upon by an unbalanced resultant force. So all forces are balanced unless we put an unbalance onto it by hitting it, by causing motion to it. The same thing happens with an object in motion. So a ball flying through the air has constant velocity, it has constant speed, it has constant direction until a force acts upon it, which could be gravity, could be weight, could be air resistance, could be it hitting something. Any of those forces can cause this constant velocity to not be constant anymore. Okay, so that's Newton's first law. Then we move on to Newton's second law, which is F equals ma. So Newton's second law is the one with the equation, the one we can actually do maths with. So F equals ma, force equals mass times acceleration. And we're talking all about proportionality and inverse proportionality. So the acceleration of an object is proportional to the force and inversely proportional to the mass of the object. So the acceleration is proportional to the force, the acceleration is inversely proportional to the mass. Proportionality means that if one thing doubles, the other thing doubles. Inverse proportionality means that if one thing doubles, the other thing does the opposite, so it halves. Then kind of a subsection from the second law is this idea of inertial mass. How hard is it for us to move this object to cause the same acceleration of an object with a lesser mass? So we take the example of the car and the tennis ball. We have to put in a lot more effort to the car to accelerate it the same amount as a tennis ball. because it has a greater mass, it has a greater inertia, it needs a bigger force to cause the same acceleration as the tennis ball, which has a lesser mass, a lesser inertia, and therefore a lesser force needed to cause the same acceleration. Then we went on to Newton's third law, which talks about every action has an equal and opposite reaction. So any two objects that come into contact with each other have an action and a reaction. So a swimmer's foot off of the side of a pool, you simply touching a wall, something simply resting on a table, so a water bottle simply resting on a table. The water bottle exerts a force on the table exerts a force on the water bottle. So they're Newton's three laws. You need to be able to define them, apply them to examples, so cars, tennis balls, anything in motion, you need to be able to describe it with respect to a law. And you need to be able to do calculations with F equals ma, as well as for higher tier, knowing what inertial mass is and how we define it and applying it to scenarios. So Newton's laws are really all about you applying it to different real life scenarios. So that's why I say to kind of take a step back, forget about the formal definitions, forget about the exam questions, and just put yourself in a real life position. What would actually happen? And then taking it back to the exam, thinking about the formal definitions and how you can construct your answer. Okay, so we're going to move on now to the second section of the webinar, which is all about cars in motion, vehicles in motion. Okay, it's all about driving, which kind of seems weird for a Physics GCSE, but it's actually probably the most relevant part, and it is going to become quite important for you guys in maybe 1 or 2 years' time. So it's really important, not only for the exam, but actually in real life. So stopping distance, it's all about this idea of stopping distances. How long does it take for a car to stop? And you can imagine this is obviously a very important topic because it can be very dangerous if we don't properly understand how long it's going to take for us to stop our car. So we have this idea of a stopping distance, which is made up of two things: the braking distance and the thinking distance. Now, the thinking distance is defined as the distance that the vehicle travels whilst the driver is reacting. So whilst the driver is, for example, reacting to seeing a traffic light, there's going to be a certain distance that the car does whilst the driver's thinking about starting to brake. So the driver's seeing the traffic light, he's starting to think, okay, I need to brake, and that is called the thinking distance, the distance that the car moves while the driver is thinking about braking. Then we have the actual braking distance, which is the distance that it travels whilst we're braking. So whilst we're slowing the car down, it's obviously going to travel a distance before it comes to rest at the traffic light. So stopping distance is made up of braking distance plus thinking distance. Now you can imagine that thinking distance is can be quite a lot smaller than braking distance, but actually that's not the reality. And you'll see that in the next slide, that thinking distance is actually a lot longer than we think, because our mind is so preoccupied with thinking, oh, I need to brake, I need to brake, I need to brake, and it doesn't realise the car is still moving in that time. So that's why it can be so dangerous if we don't realise our own thinking distances. Now, the greater the speed of the vehicle, the greater the stopping distance for a constant braking force. So if you're doing 70 miles per hour on a motorway, it's going to be much, much harder to stop your car than if you're doing 10 meters per second just pulling out of your drive. Okay, so that's the kind of idea that governs this whole thing, and the dangers around stopping distances is that if you are doing a much, much greater speed, it's much harder to stop your vehicle, okay? Which is the whole kind of reason that we have speed limits. So the greater the speed, the greater the stopping distance. Okay, so we need to know some typical stopping distances for an average car in normal conditions. Now, the reason that I say an average car in normal conditions is an average car with an average amount of wear, average brakes, average tyres. Tyres are not necessarily bad, they're not necessarily really good, just an average car. Normal conditions, it's not wet, it's not icy, there's no glaring sun. Okay, so normal conditions, average car, typical stopping distances, what we can expect at each different speed. So we have a speed distance graph here. Now, what this tells us is we read off the y-axis for a certain speed. So let's say we're doing 20 miles per hour. The red shows you the thinking distance. The blue shows you the braking distance. And you can read off at intervals of 10 of speed in miles per hour. So for 20 miles per hour, we can see that the thinking distance is 6 meters. The braking distance is also 6 meters. Okay, so for a low speed, the thinking distance is actually the same as the braking distance, which is why I said it's not always the case to think about thinking distance is much smaller than the braking distance. So at a low speed, such as 20 miles per hour, we need to know the thinking distance, the braking distance, and therefore the total stopping distance. Traveling at 40 miles per hour, the thinking distance now doubles. So if we double the speed, we can see that the thinking distance doubles. And if we double the speed, the braking distance times this by 4. Okay, so it goes from 6 to 24. So if we double the speed, we do double the thinking distance, but what's more important is that we times by 4 the braking distance. We quadruple the braking distance just by doing double the speed. Okay, so it's important that you know this relationship to be able to remember typical stopping distances. So how I suggest that you remember this graph, because you do need to know all the typical values for every single speed from 20 to 70. Okay, and it can be a lot to remember. So don't suggest that you remember the distances themselves. So don't remember like 12, 24, 36. Just remember the rules, which are if you double the distance, you double the thinking distance. If you double the If you double the speed, you double the thinking distance. If you double the speed, you quadruple the braking distance. I'm going to come back to that in a second. Okay, so reaction time. Reaction time is a really, really important aspect of experiments for all scientists. Reaction time can really, really skew an experiment. If somebody's tired that day, if they're under the influence of alcohol, if they're under the influence of drugs, or if they're simply just distracted by something else, reaction time can become a lot longer than it's supposed to be. Okay, which can, as you can imagine, really put an experiment's results out. So reaction times do vary from person to person. Children generally tend to have a better reaction time than older people. Typical values range from 0.2 to 0.9. As I said, a reaction time can be affected by a number of things such as drugs, alcohol, tiredness and distractions. So you can imagine that this, when we link it back to thinking distance, is going to have a big effect. So thinking distance can be influenced by alcohol, by drugs, by distractions, by reaction time. So if you have a slow reaction time, so for example, a traffic light, that's going to increase your thinking distance. Now, how do we measure reaction time? We need to know how to measure reaction time so that we can account for it in experiments. So the simple method that we teach and that we use is dropping a ruler between someone's open thumb and forefinger. So you've got person A and person B with a ruler. So you're simply just going to let person B drop the ruler, and then wherever you catch it, that's your reaction time. Okay, so you get it at a certain distance, which you can then convert into a time. So the higher the reaction time needed to grasp the falling ruler, the further the ruler falls before being stopped. So let's say it takes you, your reaction time is really bad, and so you grab the ruler down here. That's a worse reaction time than grabbing the ruler up here. Okay, so that's our simple method to measure reaction timing. You can also do it online. So it's like a button that turns red, and you click it, and that's the reaction time, and it gives you reaction time online. So you can also do it online. So longer reaction times can really impact thinking distances. Okay, so here's the rule that I was talking about earlier. If a car doubles, the thinking distance doubles, but the braking distance increases by a factor of 4, which is why it can be so dangerous if we don't understand that by increasing our speed, by doubling our speed, we increase our braking distance by a factor of 4. Okay, so it's really important that we understand that as drivers, so that we kind of understand and are aware of our surroundings and how long it's going to take us for us to brake and possibly avoid an obstacle. Okay, so what factors affect braking distances? So we're not talking about thinking distances anymore. The factors that affect thinking distances are tiredness, reaction time, drugs, alcohol, distractions. The factors that affect braking distances are the road and weather conditions. So is the road kind of gritty? Is it really smooth? Is it an icy condition? Is it wet? That's going to affect our braking distances. And the condition of the vehicle. So how are the brakes? How are the tyres? Are they in good condition? Are they in bad condition? Those are the only 2 factors that affect braking distances. Okay, so the wear of the vehicle, the road and weather conditions. This is a very common GCSE question. Now we need to know these 2 kind of ways of describing what actually happens when we apply a force on the brake. So what actually happens when we brake? So we apply a force to the brakes as humans. Now there is work done by friction between the brakes and the wheels. Work done is this idea of a force causing motion. So there's work done by friction between the brakes and the wheels. So we apply the brakes and we create friction. This reduces the kinetic energy of the car and it slows it down. The temperature of the brakes increase. The faster a vehicle travels, the greater the braking force needs to stop it. We know that. If a vehicle is traveling at a high speed, it needs a bigger braking force to stop it. So we need to slam the brakes harder than if we were traveling at a slower speed. But a greater braking force produces a higher deceleration. If that makes sense. If we slam the brakes, we're going to come to a much quicker, we're going to quickly come to a very slow speed. So a high deceleration. We quickly go from a high speed to a low speed if we brake really hard. But large decelerations are bad. We don't want to be slamming the brakes if we can avoid it. Large decelerations cause the brakes to overheat. And we don't want that. We don't want the brakes to overheat because the driver could therefore lose control. Okay, so factors that affect braking and factors that affect thinking are 2 separate things, and we need to know how to differentiate between both of them. So that is all of the content. I'm going to answer some of your guys' questions now that have been coming through the chat, and then we can go through some questions after that.
Preshayla,
Yeah.
so we've got some questions. Did you want us to go through some of the questions now?
Yeah.
So we've got someone asking, doesn't the thinking distance depend on each person? For example, an old or a younger person?
Okay, so yeah, the thinking distance absolutely does depend on the person. However, the thinking distances that I showed you are just average person, average car, average conditions. But yes, the thinking distance can be affected by a number of factors, such as reaction time, tiredness, drugs, alcohol, distractions. And because it can be affected by reaction timings, a very old person is going to have a longer reaction time than a younger person. So yes, the thinking distance will depend on age to a certain extent.
Perfect, thank you. Just before Prashayla goes on to some of the other questions, I can see that some of you are asking about subjects that will be added, or even new levels like A-level or Key Stage 3. So we are currently working on that, but please do make sure you're signed onto the online school email mailing list if you're not already, because that way you'll be able to kind of get updates as to new developments, and you also receive the weekly timetable of the subjects that will be delivered each week. Someone asked what other science topics we cover. We also cover biology and chemistry. So again, make sure you're signed up to that mailing list if you're not already, so you can get that information. I think you've got some more questions in the chat, Prashayla.
Yeah, so what if they have a condition? If they have a condition which affects their reaction time, then yes, absolutely. But it's not something that you'd write in an exam, okay? So you wouldn't write if the person has a condition that will affect their thinking distance. It's too vague because we don't know what the condition is and we don't know how it affects the person. So the factors that we tend to stick to for exam questions, for the factors that affect thinking distance, is alcohol, drugs, tiredness, that kind of thing. So if you stick to them, you'll be fine, because examiners are quite kind of picky with which ones they allow and which ones they don't. So that's why I say to kind of stick to those four, just in case. Okay. Someone says, what does inertia mean again? Well, inertia is just how hard it is. The inertial mass is how hard it is for us to move an object to cause a certain acceleration. Inertia is why things tend to stay as they are. So inertia is this word that we use to help us understand why things stay stationary if they started stationary, or things stay in motion if they are moving. Okay, so that's all the questions I'll answer for now. Let's go through a few quickfire questions for the last 10 minutes to consolidate our understanding. So what is the relationship between acceleration and force, and what is the relationship between acceleration and mass? You're going to have to think back to Newton's second law, which is F equals ma, and how they're related. If you don't remember, you can use the numbers to help you. Remember, if mass is constant and we have an acceleration of 4, if we double the acceleration, what happens to the force? So which answer is the correct one for the first one? Cool. So F and A is directly proportional, because if one changes, the other one changes in the same way. So if force doubles, acceleration doubles. And then for the second one, what is the relationship between acceleration and mass? Well, acceleration is inversely proportional to mass. Okay. So that means if acceleration changes, doubles, then mass halves. Okay, so what does Newton's first law of motion state? And Newton's second law of motion is summarized by which equation? So put your answers in the chat. What is the answer to each question? Okay, so Newton's first law of motion says that objects with balanced forces acting on them will stay at rest or in constant motion until we put an unbalanced force on it, and therefore it will move and not be in constant motion or stay at rest anymore. Okay, and which law of motion can be summarized by which equation? So the second law of motion is either m equals f divided by a, f equals ma, or f equals m divided by a. So that one is f equals ma. What happens if the resultant force in a car is in the direction in which it is traveling? So if the force matches the direction of the car travel, what happens? Will it increase in speed? Will it decrease in speed, or nothing? Cool, it will increase in speed, so it will accelerate. It's another way of just saying acceleration. So remember, force, the resultant force, whatever direction the resultant force is in, is the same direction the acceleration is in. How do you calculate resultant force? You're going to add together all the forces that act upon an object. So let's say we have a car. I'll just draw it as a box. Obviously that's not a car, but just pretend it is. So we have a force going forwards, let's say of 6 newtons. We have another force of 3 newtons. This can be whatever object you want. It doesn't necessarily need to be a car. And then we have a resistive force, or a force facing the opposite way, of 2 newtons. Okay, so we do this by adding up all the forces. So we're going to add the forces in one direction and take away the forces in the other direction. So 6 and 3 is 9, but then we have a force acting in the opposite direction, so we have to take it away. So 9 minus 2 is 7. And therefore 7 newtons is our resultant force. 7 newtons will be going towards the right because it's a bigger force on the right than it is on the left, so the overall direction will be to the right. Okay, and which of these statements about Newton's third law of motion is correct? Which one of the statements about Newton's third law is correct? The forces are always contact forces, the forces act on the same object, or the forces act on 2 different objects. So the forces are always contact forces. Newton's third law works because 2 objects are in contact with each other. Which of these would not increase braking distance? Which would not increase braking distance? Drinking alcohol, because drinking alcohol affects thinking distance, not braking distance. Braking distance is only affected by 2 things: the weather conditions and the wear of the car. So are the tyres in good conditions, and are the brakes in good condition? So anything to do with kind of things that affect your brain and the speed at which your brain thinks and behaves is thinking distance. So drugs, tiredness, alcohol all affect your ability for your brain to process information. But anything that actually affects the car and how quickly the car slows down is to do with the brakes, the tyres, the weather conditions. Okay, how do you calculate stopping distance? Is it thinking distance plus braking distance, thinking time plus braking time, or thinking distance times braking distance? So, yep, thinking distance plus braking distance is stopping distance. How can we reduce the braking distance? That's better brakes. Okay, better brakes, because remember, the only two things that affect braking distance is brakes and tyres and the weather conditions. So the only way that we can reduce the braking distance is by having it not rain, which obviously we can't control, or by having better brakes, better tyres. Okay, what is the inertial mass of an object that accelerates at 6 meters per second squared when pushed by a force of 100 newtons? So if you are higher tier, the equation F equals ma, the mass in this equation is the inertial mass, because the inertial mass is defined as the ratio or the division of F over A. If you're foundation, then don't worry, the mass was just the mass for you. But if you are higher tier, you need to know it as inertial mass. Now, this is the equation that we use to calculate inertial mass, which is F divided by A. We have a force of 100 newtons, which we divide by 6. So when we do 100 divided by 6, we get 16.67 kilograms. Okay, so just a simple division of force divided by acceleration to find the inertial mass. This question could also be posed as what is the mass? Simply the mass. Okay, so we need to know that the two can be exchanged with each other. Now, how can we reduce the thinking distance? So remember, this is all to do with how our brain processes information. So do we have better brakes? Should we drink a cup of tea? Or should we reduce the object's mass? Think really carefully about this one. Better brakes would increase the condition of the car. So we'd therefore be able to reduce the braking distance. Reducing the object's mass will allow it to brake quicker, but the thinking distance, the only thing that affects us as a person is by drinking up a cup of tea. Okay, and the reason that that works is because tea has caffeine in it. If you have sugar in your tea, that can also make you more alert, make you more energized, and therefore your reaction time and your alertness, your awareness will be better. So we can reduce the thinking distance. Might seem kind of like a silly answer, but it's definitely a method of reducing the thinking distance. So we'll stop there. If you do want some more access to past paper questions, just go on Physics and Maths Tutor. They're all on there. Hopefully you've had a good webinar and learned lots.
Amazing. Thank you, Preshayla, and thank you everyone for joining us. Remember that all sessions are recorded, so you can go to a YouTube channel to rewatch in case you missed any bits here. Yeah, that's it for us. Have a lovely rest of day, guys. Bye.
Thank you. Bye.